Okay, let's start the morning session of the second day of the workshop. I'm Chalmin Kim from the nearby city of Ulsan. We have two speakers. I'm not supposed to talk about soccer, am I? Okay. So the first speaker is Atsushi Mochizuki from Kyoto. He will be talking about biological function and functional module originated in structure of network. Please.
Yeah, thank you very much for kind introduction. And good morning, everyone. So it's my great pleasure to come to such beautiful place and to join such exciting meeting. So let me thank for organizers, Hirono-san and Kim-san, for giving me a chance to talk in this nice conference. So this is my title. So biological function and functional module originated in structure of network. So let me start from my personal motivation. So I have studied dynamical behavior of complex network systems observed in biology. So in modern biology, we have many examples of network which show a large number of the biomolecules and the interaction between them. And so it is believed that based on such networks, dynamics of the molecular activities run. I mean, so temporal change of gene expression patterns or temporal change of the concentration of the chemicals. And the dynamics are considered to be origin of the biological functions. So we mathematical biologists receive very high expectation from biologists. Please discuss, please identify dynamical behavior from experimentally determined network. But of course, it is not easy to discuss dynamics based on network structure alone. So because the network is just a framework about dynamics, it does not provide any qualitative detail, like functions or parameters and so on. So we usually develop mathematical models under the assumption. But we adopt different approach. So we develop some theories, mathematical theories, which rely only on the structure of the network. And by using these theories, we can determine some aspect, important aspect of dynamic behaviors just from the network without assuming models. And I think so this is very strong to connect structure and dynamics, providing logical understanding to biological systems. So today I will give you a story based on second and third theories. They are for theory for reaction network. So I will show you one extreme example of reaction network like this. So this is so all of the reactions occurring inside of human cells. So this is obtained from a famous database, KEGG. And you can see so many dots. So each dot indicate chemical substance, and so segment between connecting dots indicate reactions. Okay, and of course it is very complicated. But so I want you to focus on another interesting point. So this is carbon metabolism, and this is a sub-circuit related to lipid metabolism. This is nucleoside metabolism. This is amino acid metabolism. I mean, there are many different biological functions, but the system itself is a single connected network. So I have a question. How organisms control different functions generated from a single connected network? So this is also my focal questions in my talk, okay? So let me focus on a little bit in detail. So this is carbon metabolism, as I showed you so in the first example, this part, okay? And so of course, so reaction network is a graph showing state transitions by reactions here. So, or for example, here, So alpha glucose is transposed into beta glucose by a reaction, okay? And each reaction is mediated by an enzyme. So GAL-M enzyme in this case, okay? And the network structure is, of course, interesting, but more important is dynamical behavior of chemical substance based on this network, okay? And how organisms control dynamical behavior of based on such network. So it is realized by changing activity or amount of the enzyme. For example, so organism can change expression level of enzyme, which should influence substrate concentration or product concentration. Okay, so this is a naive idea, but basically it is true. Okay, and how we consider dynamics of chemical reaction network. So there is a long history, but so basic idea is very simple. The change in concentration in a system is determined by difference between total influx and total outflux. For example, in this small circuit, chemical A increases with flux of reaction 1 and reaction of inverse 2, and decreases with reaction of flux 2. So I called flux, which is also called reaction rate. And the reaction rate function is often modeled by assuming Hill function, Michaelis Menten function, or mass action kinetics. But in my talk, I will not assume any mathematical formula for each reaction rate function. So we just introduce a single assumption. So reaction rate depends on chemical concentration. For example, here a reaction to connect from chemical A to chemical B. So reaction rate of 2 should depend on the concentration of chemical A. So in addition to substrate chemical, there may be some chemical which regulate reaction 2. In that case, we integrate regulator chemical into the argument of reaction 2. So each reaction rate depends on substrate or regulator chemical. So this is our assumption. Okay? And each reaction has a single parameter, K, corresponding to amount or activity of enzyme. And now we focus on our problem, how steady state of concentration of each chemical, I mean UN, depends on change in reaction parameter, Kj. Okay? Yes? Kj is reaction parameter associated to reaction J.
So the capital K in the denominator, so is it a reaction parameter?
Do you mean this one?
Yeah. Hill function in the Hill function in the denominator, there is K to the N.
Yes, this is one example. So I assume the reaction parameter is more. Other distinction is more so general. So partial derivative of Rj with respect to Kj is positive.
Okay.
So any parameters which has such property. Okay, so this is just one example.
Thank you, Professor.
If you don't mind, you can remove your face mask. It's a speaker's privilege.
Oh yeah. Okay. Thank you very much. Yeah. Okay. Let me continue. So, and yes, I missed to explain as a bottom part. So this relation between change in concentration of chemical and so difference between fluxes can be summarized by introducing a matrix which is called the stoichiometry matrix. Okay. So this is just summary of the above expression. Okay, so this is our method, structural sensitivity analysis. Okay, so we start from assumption of steady state both before and after perturbation of K. Okay, and by taking derivative of steady state condition with respect to change in K, we obtain this equation. And the second equation is just summarizing the first equation in a form, in a matrix form. Okay, and practically our method is just two steps. So we first construct a matrix, which we call A matrix, from structure of the network, and calculate inverse of A matrix. Then each entry in sensitivity inverse matrix gives change in each chemical from A to D, A, B, C, D, to the change in parameter from 1 to 6. 1, 2, 3, 4, 5, 6. Okay? And so what important point is that, so this is an example of A matrix corresponding to, and the zero or non-zero distribution of A matrix directly reflect structure of the network. Okay? And this is our message. So we can determine a qualitative response of reaction systems to the perturbation of enzyme from structure of the network alone. It implies that, so we can determine zero or non-zero of sensitivity matrix from distribution of non-zero entry in A matrix. And in many cases, so we can also determine plus or minus of so inverse matrix from a structure of so A matrix. So I will show you one example, simplest example. So we have influx to our systems, and after two-step reactions, chemical C goes out from our systems. And let us consider perturbation into reaction 2 from A to B. So we increase amount or activity of enzyme corresponding to reaction 2. And what will happen at steady state? And almost all people answered like this. So downward chemical B or C may increase, and fluxes in downward 2, 3 may increase. But actually, it's not correct. This is answer. So there's no change in downward chemical, and no change in any fluxes. Only substrate chemical shows a decrease in its concentration. And it is always true without depending on the choice of the reaction function. But after assuming increasing function for reaction rate, we always observe dynamics like this. Actually, soon after increasing the reaction rate of reaction 2, reaction parameter of reaction 2, we observe increase in flux of 2 and downward chemical like this. But they are temporal. They soon converges to original level, and come back to original level. At the same time, so we see a decrease in substrate chemical like this. So we can interpret it like this. Increase in a reaction parameter is compensated by decrease in substrate chemical, and there's no change in downward after all. Okay, and this kind of the behavior is actually universal. So let me show you a little bit difficult example. Here we have a feedback from chemical C to A, and chemical C has two reactions, so branches. So let us consider perturbation to each of two reactions from C. When we increase reaction rate of reaction parameter of reaction 4, we will observe response like this. So reaction 4 and 5 to 3 increase in their fluxes. And yes, all chemicals on the pathway, DAB, show or increases. Okay? But chemical C is silent. It's very interesting. And also, what will happen when we increase enzyme mediating reaction 6? We will observe response like this. We observe decrease in flux of reaction 4, 5, 2, 3, and decrease in chemicals in the pathway D, A, B, and C. Okay, so we gave a perturbation of two reactions from chemical C, but so responses are completely asymmetric. And you may in left case, so we observed increase in direct downward of the part of the reaction, but in right case we observe decrease in side branch of the part of the reaction. Okay, and you may consider that. So non-zero response patterns may be similar between left and right, but please be careful. Chemical C shows decrease in right, but no change in left. So these so interesting characteristic responses could be perfectly explained by our finding law of localization. Okay, in Japanese, 原極則. Okay, so network may be very large, connecting. But let us focus on substructure of the network. Okay, and there are two conditions. First, we select chemical subset. After selecting a subset of the chemicals, all of the emanating arrow of the selected chemical should be selected into reaction subset. Okay, this is the first condition. And second condition is interesting. Let us count number of the element, number of the chemicals, and the number of the reactions, and the number of cycles in substructure. So if this index gives 0 value, then it is buffering structure. The buffering structure implies that any perturbation inside, any perturbation into a reaction parameter inside influences only a concentration of inside the chemical and fluxes of inside reaction only. There is no change in outside chemical or outside reactions at steady state. And this index is, of course, analogous to Euler characteristics. Okay, so Euler found that so this index governs the homology of the polygon in 18th century, but also we found that the same index governs extent of the parameter influence in chemical reaction network systems. So this may sound something mysterious, but actually a mathematical proof is very simple. So actually a buffering structure corresponds to a square non-zero block in A matrix. So downward of this square should be 0. Okay, and so proof is very easy. It can be understood even so by an undergraduate student. Okay, so let us go back to our example. So in example 1, this is buffering structure. One chemical, one reaction. Of course, no cycle satisfies our condition. And in example 2, left case, this is buffering structure. 3 chemicals and 4 reactions. And actually, a cycle is defined in a reaction space. So all 4 reactions construct one cycle. 3 minus 4 plus 1 satisfies our condition. And in right case, we should note this buffering structure. 4 chemical, 5 reaction, 1 cycle satisfies our condition. So important point is that buffering structure is a kind of the functional module or a module of regulations, which is naturally determined from local structure of the network. And it is not only a mathematical concept, but actually so very important in biology. So we know some example of the actual network systems where buffering structure take an important role. So I will show you one example. So it is cell cycle systems. So cells have multiple phases in their life from their birth to another cell division. So G1, S, G2, M. Okay, and so cell cycle is actually a mechanism to stop the process until all of the preparations are completed. In case of yeast, there are 2 checkpoints, G1S and G2M. And so by the increase of the special protein complex, cyclin CDK complex, these checkpoints are passed. So okay, so let me explain a little bit. So complex is formed from CDC2 and another regulator. And amount of the CDC2 is kept constant all through the life of cells. And so regulator substructure cyclin change with time. For example, by the increase of the G1S cyclin, G1S complex is generated. And by the increase of the G2M cycline, G2M complex is generated. So this is the understanding in textbook. But I thought that this system is a little bit strange. So this is also reaction network. And you can see also G1S complex and G2M complex are connected in a single network. And so I said amount of the CDC2 is kept constant. So actually there are 6 protein complexes in this network. It implies that the total amount of these 6 should be kept constant with time. And we may expect that if one of the complex increases, it may induce decrease in another counterpart. But actually, by the analysis, structural sensitivity analysis, we do not have to worry about this kind of the interactions. Okay, they are actually completely independent. So there are only 2 reaction parameters which influence amount of the G1S complex. And there are only 6 reaction parameters which influence amount of the G2M complex. And these 2 parameters are clearly, completely disjoint. So I will show you dynamics, okay, based on analysis. So we calculated the dynamics based on this network. And so while calculating the dynamics, so we change parameter value of synthesis rate of G1S cycline and G2M cycline. Okay, and please focus on this bottom graph. So this is G1S complex and this is G2M complex. You can see that. So when G1S complex shows drastic change, increase, decrease, the counterpart is completely silent. And when G2M shows drastic change, increase, decrease, the counterpart is completely silent. So it implies that these 2 protein complexes are controlled completely independently. And this independent regulation is realized not by choice of the parameters, nor choice of the functions, just from structure of the network. I mean, there are buffering structure like this, like this. So these 2 complexes are controlled independently by the different regulatory modules. Okay, so independent regulations realized by different buffering structures. So detail will be explained by Dr. Yamauchi in poster. Okay, and I want to show you our recent progress, the theoretical progress in our theory. So it is equivalence between a Jacobian matrix and A matrix. So this is the definition of our A matrix, and this is the Jacobian matrix. And you can see some similarity is between these 2. Actually, we proved that. So characteristic polynomial can be constructed from A matrix, similarly as Jacobian matrix. And instead of the identity matrix, so we have to introduce another integer matrix rho. But rho is constructed easily from metric matrix like this. Okay, and this result implies so we can obtain the same eigenvalue from this polynomial, and these 2 polynomials gives eigenvectors, and eigenvectors has one-to-one correlations between these 2 expressions. Okay, and this mathematical results, of course, gives multiple directions of the mathematical progress. So first one is we can discuss steady state identifications from determinant A, not determinant J. Okay, and we may also discuss condition for the existence of stationary points, but today I will focus on this first direction. There are 2 major advantages of using A matrix instead of Jacobian matrix. First one is that we can discuss condition of bifurcations from network structure. I mean, so Jacobian matrix does not have clear structure corresponding to network, but also by in a matrix we can see a network structure in this A matrix structure in the non-zero distribution of non-zero entries. One non-zero entry in A matrix corresponds to one arrow in reaction network. And the second advantage is, of course, coming from buffering structure. So I said that buffering structure is a square non-zero block in A matrix, so which of course implies determinant of A can be factorized like this. So determinant of A gamma corresponding to buffering structure, and the determinant of A gamma bar corresponding to remaining part. Okay, of course this implies determinant of A equals 0 is equal to this one equals 0 or this one equals 0. Okay. So let me explain using one example of network. This is small reaction network, including 3 chemicals and 5 reactions, and blue indicate regulation. And this is of course small, but also it already include buffering structure here. Okay, and so A matrix is written like this. So this is also a square non-zero block, and the determinant of A can be factorized like this. Okay, so bifurcations can be identified either this term equals 0 or this term equals 0. Okay, and the first term implies that. So by the balance between R2A and R3A, bifurcation will take place. Okay, so in this way, so we can discuss bifurcation condition structurally by decomposing into smaller substructure based on buffering structure. In addition, we can discuss parameter range which can induce bifurcation behaviors. So it is directly a result of the law of localization. Okay, so law of localization implies that the parameters inside buffering structure do not influence outside. So determinant A gamma equals 0 can be induced by all of the parameter in a system, but so determinant A gamma bar can be induced just by parameters outside of buffering structure only. Okay, and so we can also determine the range of the chemical set which shows bifurcation behavior. Okay, so when determinant A gamma, it is also determined from the support of the null vector of A. Okay, when determinant A gamma takes 0 value, we will observe bifurcation behavior only inside of the buffering structure. And when also determinant A gamma bar takes zero value, we will observe all the chemical inner systems. So I will show you a demonstration after assuming the reaction rate functions. So first let us focus on this case. So determinant A gamma takes 0 value. In this case, we should observe 0 value bifurcation behavior only inside of the buffering structure. Actually, we observed this case. So when a determinant A gamma takes 0 values, only a chemical A shows bifurcation behavior like this. And please note that B and C are silent, even though they are downward of chemical A. So even though chemical A shows very drastic change, they are silent. Okay. And let us see another case. So when determinant A gamma takes 0 value, in this case, all of the 3 chemicals should show bifurcation behavior. So actually, so we observed such behavior like this. Determinant A gamma bar takes 0 value, and all of the 3 shows bifurcation behaviors. And let me emphasize that. So these 2 are only cases. So we can discuss possible bifurcation patterns from network structure only. And yes, structural analysis provide these two are only possible bifurcation patterns in these systems. Okay, and so this kind of analysis, bifurcation analysis by decomposing systems into small subject structures should be powerful if a system has larger number of the buffering structure. So I will show you such an example in the last of my talk. So this is a carbon metabolism network, including 35 chemicals and 45 reactions. And this network has 17 buffering structures, and they are nested like this. Okay? So yellow part. So actually, yellow part corresponds to pentose phosphate pathway. It is a buffering structure. So any perturbation into yellow or influences only 3 chemicals in yellow. And red and yellow is buffering structure. So perturbation in red influences only 4 chemicals in red and yellow. And yellow plus orange is another buffering structure. So perturbation in orange influences only 4 chemicals in orange and yellow. And blue is buffering structure. So perturbation in blue influences blue chemicals. And finally, perturbation into green reactions influences green, red, orange, yellow, and blue. So we can see that existence of buffering structures generate modularity in regulation. And so nest of the buffering structure produce hierarchy in regulation. Okay. And similarly, we see a hierarchy in bifurcation behaviors. So there are 17 buffering structures. So we can also decompose a bifurcation condition into 17 terms. So we examined each of them, and we found that only a single term can take 0 value. The other 16 terms do not show sign change. So we should focus only on this one, determinant A gamma red. Okay, and the determinant A gamma red takes 0 value only by the parameter change in red and green. And when also this term takes 0 values, we should see a bifurcation behavior in chemical in blue and red only. And by numerical search, we observed such behavior. Okay, and let me repeat again. So theoretical analysis based on network structures gives us that. So this is only a single pattern of bifurcation of these systems. Okay, and let me summarize my talk. So both sensitivity behavior and bifurcation behaviors of reaction networks can be determined from network structure alone. So it implies that both continuous change and discontinuous change to the change in parameter can be discussed from network structure only. So almost all can be determined. Okay, and the buffering structure is of course very important, and it is naturally generated from local structure of the network, and it strongly governs the parameter regulations. Okay, and so we can expect that buffering structure may be origin of the biological behavior, origin of the modularity and hierarchy in real biological systems. So I show you very large systems which shows multiple functions, but multiple different functions might be regulated separately, independently by the existence of the buffering structure. Okay, so this is very last slide. So our project was supported by many collaborators. So I want to express my sincere thanks to all of the collaborators. And so thank you for your attention. I'm very happy to receive your questions. Thank you very much.
Thank you very much for being on time. We have more than 10 minutes. Jinsu.
Thank you. It's a very impressive talk. I remember one slide that contains the CDC2, CDC3, the enzymes. Could you go back the slide?
Yes, yes.
Yeah, thank you.
Maybe this one?
Maybe
maybe-
go a
oh,
little
yeah.
more. Yeah, here.
Mhm.
So my understanding is the buffering structure, I mean, the rate parameters in buffering structure preserves the steady state of the variable outside the buffering structure. So what is the x-axis in the plots on the bottom to the two plots? Is it time or?
Yes. So is horizontal axis is so time.
So I think if you perturb those enzyme parameters,
Mhm.
then the transient dynamics is also
Mhm.
perturbed, and then it goes to the same steady state. That's my understanding, but there is no such perturbation in the plot. That's my question.
Yeah. Thank you very much. Yes. So our theory can be applied. So behavior of the steady state, and so transiently, so we may observe temporal change, but also in this figures to clarify our result. So we measure the result. So with a sufficient time of the intervals. So this graph shows change in quasi steady state. So temporary G1S may show also small change to the perturbation of the synthesis rate of the G2M cycling. But also we ignored by taking the sufficient time to measure the result. Yes, it's important.
Thank you.
And so maybe from biologically, assumption of the steady state can be confirmed. So because change in enzyme activity, change in enzyme expression is very slow than reaction. Yes.
Thank you for the interesting talk. I have two small questions. So first one is about hierarchy in buffering structures. So do they make partially ordered set structures, or is it just an example of hierarchy?
So I might miss. So are you asking the generality of the hierarchy?
Yes.
Yes,
Is it
universality of the hierarchy. So actually, so I also ignored important mathematical result. So actually, so we can we proved that intersection of two buffering structure is always buffering structure.
Okay.
So we always observe the hierarchy.
Okay.
So if there exists multiple buffering structure, they may be a delay in relation of the inclusion relation, or if there exist intersections, it should be another buffering structure. So we always observe this structure, so hierarchy structure.
Okay, thank you. Another question is that when you mentioned about bifurcation, if I understood correctly, I say that bifurcation should be occurring inside buffering structure. But is it necessary to have all the variable inside of buffering structure have bifurcation?
So mathematically, it's unclear. We don't know. Yes, sensitivity response and behavior, bifurcation behavior is confined in buffering structure. But we cannot say all of the members inside buffering structure should show behavioral change. We cannot say.
Okay.
So so I may show you one example. So so this is these simplest examples already include such cases. So flux we do not observe flux change here and here. So we may intuitively understand. So because also this is flux. So for the confinement of the response, this reaction should not show any change. So because if this one change, so it should also influence outside. Okay. So we may we have a conjecture that reaction arrow which is going out of buffering structure is silent to the perturbation inside.
Okay, thank you.
But this is, I think so. This is only one example of the non-silent response inside the buffering structure.
Oh, yeah.
My question is about like just small about like definition of buffering structures. In this slide, when we consider example 2 in the middle, it seems like can I ask why did you skip that black dot on the bottom at the bottom? So is it like intentional thing, or like can we leave the buffering structure open? Let me see.
I'm sorry, I missed.
It seems like in the red module, let me say, in the middle is not closed as a graph, right? Because
do you mean also this one?
oh yeah, that one. And so it seems like even though there is a cycle, we just skip that black dot. Is it okay?
I see. Actually, I explained, but also my explanation might
Maybe I
be
was
very short.
lost. Yeah.
So a cycle is actually defined in reaction space. So cycle constructed by set of the reactions.
Oh, okay.
So it is our definitions. More precisely, so cycle is actually kernel of stoichiometric, coming from kernel of stoichiometric matrix.
Thank you.
Hey, thank you for an interesting talk. Maybe I missed that part. Should that arrow or the arrow, which means that a certain species affect to other species, should it be some positive? So I mean, if certain species concentration increases, does that positively increases the production of the affecting species?
Okay, so we have to be careful not to confuse between reaction network and regulatory network. So here, so we focus on reaction network, where each arrow indicates state transitions, who becomes who. And we also have another network. So it is really complicated. In biology, so we have another network, regulatory network, where each arrow indicates regulation, who controls who. So here, all of the arrow in my presentation is state transition. So we do not care whether it is positive or not or negative. So maybe we can say that. So each arrow, this arrow implies decrease this one in this increase in this one. Okay.
Okay, thank you.
Yeah, thank you for the very nice presentation. I have a question about reversible reactions. So if we want to have thermodynamics on a network, then we would like to have a completely reversible network. But yeah, of course, we know that even having small reverse rate changes the steady state completely. And does your theory also work for reversible reactions?
Yeah, yes. So from the topological aspect, so we can treat both reversible and non-reversible reactions. So for example, so this is a case of the reversible reactions, and yes, we treat there are two reactions in different directions, and this may construct small cycles and so on. But so from so physical point of view, it's very difficult to distinguish between reversible reaction and non-reversible reactions. So it's so matter of the physics, and so our theory is so after given network, so we can give mathematical conclusion like this.
Okay, thank you very much. Also, one other question for the still. You had the slide with the 3 examples that you showed before. Can I see it one? Yeah, this one. So do we, if all the reactions were reversible, do we even get more buffering structure? For example, in the middle, is this the shown one still a buffering structure? And then if I inverse the arrows, is it another one? Or do we have to include all reactions in the buffering structure?
Actually, this example 2 already has many buffering structures. So you can see the same structure in example 1 exists in example 2. Okay, here. And this small buffering structure is appears also in example 2, but I'm sorry. So maybe this is not the correct answer. So if we consider these arrows as reversible, so we can distinguish. So yes, so this is buffering structure, but also by adding inverse reactions, we will have another buffering structure, because also one arrow plus 1 cycle does not change index. So mathematically, by considering the reversible reactions, number of the buffering structure increases. But I do not have see whether it is meaningful or not.
Okay.
It's kind of the interpretation.
And for the cycles, we count all cycles or the cycle basis? When you talk about cycles, then obviously if you have inverse reactions, we get a lot of cycles.
Yes. So yeah, in general, reverse cycle induce small cycle at the same time. So one reverse cycle and 1 cycle cancel. So adding reversible reactions or not is kind of arbitrary choice.
Okay, great. Thank you very much.
So I have one question here. So are the buffering structure well defined even for regulatory networks where the impact on certain pathway may be non-monotonic as a function of regulatory protein or enzymes? Could you give us a comment on that?
Yeah, so actually, to define buffering structure in regulatory network is also kind of another problem. So we have to, before considering the buffering structure, so we have to consider how we define reaction network from regulatory network. And just naive, I think practically it's impossible. So because regulatory network has smaller information than reaction network. So it's just influence relations. And the reaction networks shows a little bit of detail about the change. So one reaction induce decrease in substrate and increase in product. So I think it's kind of the problem of the definition.
Right. Thank you. Any other?
May I ask a small question?
Okay.
So I have a question about the correspondence between the, Jacobian and matrix
Mm,
A. So in the presence of a conserved quantities, I mean the Jacobian in general has 0 eigenvectors, right?
Yeah.
So in that case, when you make this, but the matrix A is has a non-zero determinant even in the presence of a conserved quantity. Right. So when you make this comparison, I mean, do you use a bit, I mean, modified definition of Jacobian? Yes.
Yeah, thank you very much. So in short, so we haven't examined. So we proved, we gave a proof only the case without including conserved quantity. But also we expect, we can construct a characteristic polynomial similarly in the case of including concept quantity. Yeah, not yet. So we have.
Right. Then we have 10 minutes break before we resume the session with Yuji's talk. Okay, let's have a short break.
Thank you very much.
Thank you.